Hey everyone, welcome back. Ready for another deep dive? This time we're going to explore something that's all around us but we rarely stop to think about. The thermal properties of materials.
It's like this hidden world that governs how things react to heat, how they store it, transfer it, and even how their size changes because of it.
Yeah, like why a metal spoon gets hot so much faster than a wooden one. We've got a bunch of sources for this: one textbook, excerpts, journal articles, and even a patent application for some new thermal insulation material.
It's going to be fascinating to see what we can uncover.
Absolutely.
Oh.
So where do we even begin with something this broad?
Well, I think a good starting point is heat capacity. It's a fundamental concept that tells us how much heat a material can store.
Okay, heat capacity. Sounds pretty straightforward, but I have a feeling it's more complex than it seems at first glance.
You're right, there's more to it than just how much heat something can absorb. Heat capacity is really about a material's capacity to store thermal energy, and it's measured in different ways. There's specific heat capacity, which is measured per unit mass, and then there's heat capacity, which is per mole of material.
So, two ways to measure the same basic thing. Is it just personal preference which one you use?
It kind of depends on what you're focusing on. Specific heat capacity is handy when you're dealing with a known mass of material, while heat capacity is more useful when you're concerned about the number of atoms or molecules involved.
Got it. So what are some of the factors that affect a material's heat capacity?
Well, one of the key factors is the way the atoms are arranged and bonded within the material. Materials with more complex structures where the atoms have more freedom to vibrate tend to have higher heat capacities. And those vibrations are actually really important.
Vibrations, you mean like atoms jiggling around?
Exactly. Imagine atoms in a solid as tiny balls connected by springs, constantly jiggling and bouncing around. The more ways these atoms can vibrate, the more freedom they have to jiggle, the more heat energy the material can absorb.
So it's like those little toys where you push a button and the balls start bouncing all over the place. The more balls and springs you have, the more chaotic it gets.
That's a great analogy. And these coordinated vibrations, these waves of atomic motion, are actually called phonons. They're kind of like the little messengers of heat energy carrying it through the material.
Phonons. Okay, that's a new one for me. Are they similar to photons, those little packets of light?
You got it. Just like photons are the quantized units of light, phonons are the quantized units of heat energy. And the more freely they can move, the higher the material's heat capacity will be.
This is making me think about how different materials feel when you touch them. Like, metal always feels cold, even at room temperature. Is that because of its heat capacity?
That's a great observation, and it actually has more to do with another thermal property called thermal conductivity, which we'll get to later. But heat capacity does play a role in how quickly a material heats up or cools down.
Okay, so materials with a high heat capacity can absorb a lot of heat without their temperature changing too much. What about materials with a low heat capacity?
Those materials will experience a more significant temperature change for the same amount of heat. Think about water, for example. Water has a remarkably high heat capacity, which is why it takes a lot of energy to boil it. That's also why coastal areas tend to have more moderate temperatures compared to inland regions.
Yeah, that makes sense. The ocean acts like this giant heat sink, moderating the temperature swings.
Yeah.
So we've talked about specific heat capacity and heat capacity. Are there any other types of heat capacity?
Yes, there's also heat capacity at constant volume, denoted as CV, and heat capacity at constant pressure, denoted as CP.
Ah, yes. I remember seeing those in the textbook. But I was always a bit confused about the difference.
It's all about the conditions under which you measure the heat capacity. CV is measured at a constant volume, meaning the material isn't allowed to expand. CV is measured at constant pressure, meaning the material can expand freely, and usually CP is a little bit higher than CV.
Why is that?
Because some of the heat energy goes into doing the work of expansion when the material is allowed to expand at a constant pressure. It's like if you heat up a balloon, some of the heat energy goes into making the balloon bigger.
So it's like a pressure cooker versus a regular pot on the stove. The pressure cooker maintains constant volume, while the regular pot allows for expansion as steam escapes.
That's a fantastic analogy. You're really getting the hang of this.
Okay, I'm starting to feel like I'm getting a grasp on this whole heat capacity thing.
Yeah.
Are there any other important factors that affect a material's heat capacity?
There are a few other things that can contribute, but they're usually not as significant as the atomic structure and the vibrational freedom of the atoms. For example, the electrons in a material can also absorb energy and contribute to heat capacity, but this effect is usually more noticeable at very low temperatures.
So it's mostly about those jiggling atoms and their phonons.
You got it. And there's this interesting concept called the Debye temperature. Above this temperature, a material's heat capacity becomes pretty much constant. Even if you keep adding more heat, it's like the material has reached its limit for absorbing heat through those atomic vibrations.
The Debye temperature, huh? I'll have to look into that more later. It sounds like something that could be on a physics exam.
It's definitely a key concept in solid-state physics. But for now, I think we've covered the basics of heat capacity pretty well. Ready to move on to something else?
Absolutely. We've talked about how materials store heat, but what about what happens when they actually start to heat up? Do they just get hotter and hotter?
Well, yes, they do get hotter, but there's often more to it than that. Remember those jiggling atoms we talked about? As they gain more energy, they start moving around more vigorously, and that can actually cause the material itself to change size.
Wait, you're saying that heating something up can make it bigger?
Exactly. It's called thermal expansion, and it's a fundamental property of materials. As the temperature increases, the atoms tend to move further apart on average, leading to an overall increase in the material's dimensions.
So that's why things expand when they get hot. I always just kind of took that for granted.
It's one of those things that seems obvious once you think about it, but there's actually a lot of fascinating science behind it, and it has huge implications in engineering and design.
I can imagine. Like, you wouldn't want a bridge to buckle because the metal expanded too much on a hot day.
Exactly. That's why engineers have to carefully consider the thermal expansion of materials when designing structures like bridges, buildings, and even things like electronic devices. They use things like expansion joints to accommodate the changes in size.
I've always wondered about those gaps in bridges. Now it makes sense. They're there to prevent the bridge from warping or cracking as the temperature changes.
Exactly. It's a simple but brilliant solution to a potentially serious problem, and the amount a material expands or contracts with temperature is quantified by something called the coefficient of thermal expansion.
Coefficient of thermal expansion. So a higher coefficient means the material will expand more dramatically when heated.
You got it. Different materials have different coefficients of thermal expansion, and you can actually find tables that list these values. Metals, for example, tend to have higher coefficients of thermal expansion than ceramics.
So a metal rod would expand more than a ceramic rod at the same size when heated to the same temperature.
Exactly. And that difference in expansion can be really important in applications where you have different materials joined together. Like in electronics, you might have metal components attached to a ceramic substrate, and if they expand at different rates, it can create stresses that could damage the device.
Wow, I never thought about that. But it makes sense that those kinds of mismatches could cause problems. So what determines a material's coefficient of thermal expansion? Is it related to those jiggling atoms we talked about earlier?
You're on the right track. It all comes down to the strength of the bonds between those atoms. Materials with stronger bonds tend to have lower coefficients of thermal expansion because the atoms are held more tightly together and have less freedom to move around.
So ceramics, with their strong ionic and covalent bonds, would expand less than metals, which have weaker metallic bonds.
Exactly. And polymers, which have even weaker van der Waals forces between their molecules, tend to have the highest coefficients of thermal expansion.
So it's like a spectrum of expansion, from ceramics at the low end to polymers at the high end.
That's a great way to think about it. And understanding this spectrum is crucial for designing materials that can withstand temperature changes without falling apart. And then there are some really interesting materials that defy this general trend.
Oh, like what?
Well, have you ever heard of Invar?
Invar. The name rings a bell, but I can't quite place it.
It's a nickel-iron alloy that was actually invented back in the late 19th century, and it has an incredibly low coefficient of thermal expansion, meaning it barely changes size at all when heated or cooled.
Wow, that sounds pretty remarkable. Why is that? What makes Invar so special?
It's all thanks to its unique magnetic properties. As Invar heats up, its magnetic structure changes in a way that counteracts the normal thermal expansion. It's like a built-in mechanism that keeps the material from expanding too much.
That's so cool. It's like a self-regulating material. What kind of applications is Invar used for?
It's used in all sorts of precision instruments where even tiny changes in size would be a problem, like in clocks, watches, and scientific instruments. It was even used in the original meter bar, the standard for measuring length.
That's fascinating. I never realized that something as seemingly simple as thermal expansion could have such far-reaching applications.
It's a great example of how understanding the fundamental properties of materials can lead to incredible innovations. And it's just one of many examples. There's a whole world of amazing materials out there, each with its own unique set of thermal properties that make it suitable for different applications.
We've covered how materials store heat and how they change size when heated. But what about how heat actually travels through a material? That seems like a crucial part of the thermal puzzle as well.
You're absolutely right. That's where thermal conductivity comes into play, and it's a fascinating topic that we'll dive into after a quick break.
Okay, so thermal conductivity. This is about how easily heat energy can move through a material. Yeah.
Exactly. Like, imagine you're holding a hot cup of coffee. The reason you feel that warmth in your hand is because of heat transfer from the cup to your skin. And how quickly and intensely you feel that heat, well, it depends on the thermal conductivity of the cup's material.
So that explains why a metal mug feels so much hotter than a ceramic one, even if they're both filled with coffee at the same temperature. Metals are just better at conducting heat, right?
That's it. Metals are like the champions of thermal conductivity. It's all thanks to those free electrons we were talking about earlier. They can easily zip around and carry thermal energy with them, like a super efficient delivery service.
So those free electrons are responsible for both a metal's electrical conductivity, AD, its thermal conductivity.
Precisely. And there's actually a law that connects these two properties called the Wiedemann-Franz law. It states that the ratio of thermal conductivity to electrical conductivity is pretty much constant for metals at a given temperature.
So good electrical conductors are almost always good thermal conductors too.
You got it. It's a pretty neat relationship, and it highlights how those free electrons are doing double duty, carrying both electrical current and heat energy.
That makes sense.
Mm.
What about materials that don't have free electrons, like ceramics or plastics? How do they conduct heat?
Well, they still conduct heat, just not as effectively as metals. Remember those phonons, those little packets of heat energy carried by vibrations?
Yeah, those jiggling atoms.
Right, so in ceramics and polymers, heat transfer happens mainly through those lattice vibrations, those phonons. But unlike the free electrons in metals, phonons tend to bump into things more often as they travel through the material, scattering their energy and slowing down the heat transfer process.
Ah, so it's like trying to navigate a crowded room versus an empty hallway.
Exactly. And the more imperfections or disorder there are in the material structure, the more scattering those phonons will experience and the lower the thermal conductivity will be.
That makes sense. So a perfectly ordered crystal would have higher thermal conductivity than a messy, amorphous material.
In general, yes. But there are other factors that come into play as well. For example, the textbook mentions something about porosity affecting thermal conductivity.
Right, porosity, the amount of empty space or pores within a material. How does that affect conductivity?
Well, think about a brick. It's a ceramic material with a lot of pores, and those pores are filled with air, which is actually a very poor conductor of heat.
So the air pockets in the brick act like little insulators, slowing down the transfer of heat through the material.
That's exactly it. And that's why porous materials are often used for insulation. They trap air and prevent heat from flowing easily. Like, think about a down jacket. The fluffy down feathers trap lots of air, keeping you warm by slowing down the heat loss from your body.
That's a great example.
Yeah.
So adding pores to a material generally decreases its thermal conductivity. What about crystallinity in polymers? Does that have an effect too?
It does. In general, polymers with a higher degree of crystallinity, meaning their molecules are arranged in a more ordered structure, tend to have higher thermal conductivity.
So it's similar to what we were talking about with metals and ceramics. More ordered structures allow for more efficient heat transfer.
Exactly. A more ordered structure means fewer obstacles for those phonons to bump into as they travel through the material.
This has all started to make a lot of sense. We've talked about how materials store heat, how they change size when heated, and now how heat moves through them. But I have this nagging feeling that sometimes all this heat transfer and expansion and contraction can be a bad thing, right?
Whoa, you're absolutely right. All that thermal energy moving around can lead to some interesting and sometimes problematic effects. Like, have you ever heard of thermal stresses?
The thermal stresses, it sounds a little ominous.
Well, it can be. It's all about what happens when a material is restrained from expanding or contracting freely when its temperature changes.
So like if you heat up a metal rod but hold its ends fixed so it can't get longer.
Exactly. The material wants to expand, but it's being prevented from doing so. And that creates internal stress within the material. It's like trying to stretch a rubber band, but holding the ends fixed, the rubber band is under a lot of stress.
Ouch, I can almost feel that tension just thinking about it.
And just like a rubber band that's stretched too far can snap, materials under too much thermal stress can also fail. They can deform, warp, crack, or even shatter.
Yikes. That sounds pretty serious.
It can be, especially in applications where you have large temperature changes or materials that are very sensitive to thermal stress.
So how do engineers deal with thermal stresses? Do they just try to avoid them altogether?
Sometimes that's possible, but in many cases it's unavoidable. Like if you're designing a jet engine that's going to be operating at extremely high temperatures, you can't just prevent the materials from expanding and contracting.
So what do they do?
They have a few tricks up their sleeves. One approach is to choose materials that are inherently more resistant to thermal stress. Like some metals are more ductile, meaning they can deform without breaking, which helps to relieve some of that stress. Others might have a lower coefficient of thermal expansion, so they don't change size as much to begin with.
So it's about picking the right material for the job based on its thermal property?
Exactly. And sometimes it's about designing structures in a way that minimizes the buildup of thermal stresses. Like you might incorporate expansion joints or flexible connections to allow for some movement without creating excessive stress.
It's like giving the material a little breathing room so it can expand and contract without causing any trouble.
That's a great way to put it. And then there's this whole other phenomenon called thermal shock that we need to talk about. It's kind of like thermal stress on steroids.
Thermal shock, what's that?
It's what happens when a material experiences a very rapid temperature change, like being plunged into ice water after being heated up. That sudden temperature difference can create huge stress gradients within the material, leading to catastrophic failure.
Like the material just shatters.
In some cases, yes. It's particularly problematic for brittle materials like ceramics, which don't have the ability to deform and relieve those stresses like metals can.
So a ceramic dish is more likely to crack if you pour boiling water into it straight out of the oven.
Exactly. That's why it's important to be careful when handling hot ceramic objects and to avoid exposing them to sudden temperature changes.
That makes sense. So what determines a material's resistance to thermal shock? Is it just about how strong it is?
It's actually a combination of factors. Strength is important, of course, but thermal conductivity also plays a key role. Materials with high thermal conductivity can dissipate heat more quickly and evenly, reducing those sharp temperature gradients that lead to thermal shock.
So a good conductor would be less likely to experience thermal shock.
In general, yes. And a lower coefficient of thermal expansion also helps because it means the material won't change size as much in response to those temperature changes.
So it's like a balancing act between strength, thermal conductivity, and the coefficient of thermal expansion. You need the right combination of those properties to create a material that can withstand thermal shock.
You got it. It's a testament to the ingenuity of material scientists and engineers that we've been able to develop materials that can withstand some pretty extreme temperature changes without falling apart.
This is also fascinating. It's amazing how much science and engineering go into something as seemingly simple as heat.
It really is. And we've only just scratched the surface. There's so much more to explore in this hidden world of thermal properties.
And we've got a whole lot more material to go through, including a patent for a new thermal insulation material. What do you say we take a look at that after a quick break? Okay, we're back and ready to wrap up our thermal journey. We've explored how materials store heat, how they change size when heated, and how heat travels through them. Even touched on thermal stresses and shock and the whole concept of entropy. What's left to uncover in this hidden world of thermal properties?
Well, we've talked a lot about how heat moves through materials, but what about how it's actually stored within them? That brings us to thermal energy storage, a really fascinating concept with a lot of potential.
Okay, I'm intrigued. How do materials store thermal energy? It's not like they have little compartments where they keep it tucked away right.
Not compartments exactly, but remember those vibrating atoms and phonons? Those are essentially packets of thermal energy. The more energy a material absorbs, the more vigorously those atoms vibrate, and the more thermal energy is stored within the material structure.
So materials with high heat capacity are essentially good at storing thermal energy because they can absorb a lot of heat without a big temperature jump.
Exactly. And that makes them ideal for applications where you need to store heat for later use, like those hand warmers that use a salt that undergoes a phase change.
You mean those little packets you click and they magically heat up? I've always wondered how those work.
It's a clever use of thermal energy storage. See, the salt absorbs a lot of heat as it melts and then releases that heat slowly as it solidifies, keeping your hands warm.
That's so cool. So what other applications rely on thermal energy storage? Anything beyond hand warmers?
Oh, tons. Think about solar energy systems. They capture energy from the sun during the day, but what happens when the sun goes down?
Right, you need a way to store that energy for later.
That's where thermal energy storage comes in. Materials like molten salts or phase change materials can store that captured heat and then release it later to generate electricity or heat buildings, even when the sun isn't shining.
So it's like a thermal battery, storing energy for when we need it most.
Exactly. And as we move toward more renewable and sustainable energy sources, this idea of thermal energy storage becomes even more vital.
This has been a truly eye-opening deep dive into the world of materials and how they interact with heat. I feel like I've gained a whole new perspective on something I used to take for granted.
Me too. It's amazing how much we can learn from diving into the fundamental properties of materials. And who knows what other exciting applications we'll discover as we continue to explore this field.
Well said. And to everyone listening out there, we hope this deep dive has ignited your curiosity about the often unseen world of thermal properties. From those jiggling atoms to the incredible applications of thermal energy storage, we've only just begun to explore the possibilities. Until next time, keep exploring and stay curious.